Here's a video for chapter 9.3 on sample means. So in the last chapter we talked about sample proportions and that those deal with categorical data. Oftentimes they're yes or no questions or percentages. For example, what percent of the population attended church last week? Sample means deal with quantitative data. So these are numbers that we can average, like income of a household, the lifetime of a car brake pad, blood pressure of a patient, etc., etc. Okay, we'll go back to that website here in a little bit. So this is going to tie in more to what we did in class on the little applet. So averages are less variable than individual observations, and averages are more normal than individual observations. So if I go back to this and let's say I change n to 10, so I take a bunch of samples of size 10, you can see that on this bottom one here is 25. So you can see that there is less variation in samples of size 10 because I can't get an average out here. It's very unlikely if this correlates down here. I'm going to get mostly an average out of 10 numbers that's more centered around the middle. That's why the spread of this is not as much, and even more so with an n of 25. So just to kind of give you an example, when we calculate the mean and standard deviation, let's say that I wanted to investigate whether lions that were captive or in zoos were malnourished or something like that. So I would take random samples out of these lions in zoos, and I would calculate, let's say, their mean weight. So I'd take a random sample of 5 lions, and I'd calculate their x-bar. And then I'd take a random sample of another 5 lions and get their x-bar. And I would repeat this process and plot those values on a histogram. And what I'd end up with is something that was approximately normal, and that the mean of that distribution, the mean of the sampling distribution of x-bar, so mu sub x-bar equals mu. Alright, so the mean of the actual lions would be the mean of my sampling distribution. Again, that goes back to this. The mean of this graph is the same as the mean of this sampling distribution here. Okay, and I'm going to have a standard deviation of the sampling distribution, which is sigma sub x bar, and that's sigma over the square root of n. So the standard deviation of x bar of this sampling distribution is sigma over the square root of n. And again, those formulas are on my formula sheet. Alright, so if I look down here, these are the formulas for proportions. If x bar is the mean of a random sample of size n from an infinite population with mu and standard deviation, mu sub x bar equals mu, and sigma sub x bar equals sigma over the square root of n. Okay? And again, we'll go over these in more detail in class, kind of what the symbols are. So a couple other things. The sample mean x bar is an unbiased estimator of the population mean. The values of x bar are less spread out for larger samples, as shown on that applet, and the recipe for standard deviation should only be used if the population is 10 times bigger than the sample. So again, the population should be greater than or equal to 10n. Okay, now let's do some problems. So here an example when we're talking about study times of a history test or a final exam. So let's say that the average study time for a final exam in history is found to be 6 hours and 25 minutes. Again, that's the population mean. And a standard deviation of 1 hour and 45 minutes. So the first thing we want to do is turn these all to hours, because we've got hours and minutes, which isn't going to help with our calculations. So we're going to take 25 minutes and divide by 60 and get 0.42. So the mean study time is 6 hours and 25 minutes, which is about 0.42 of an hour. And the standard deviation is 1 hour and 45 minutes. So we're going to take 45 divided by 60 and convert the standard deviation into 1 point. And 45 divided by 60 is 0.75. So a standard deviation of 1.75. All right, so we just had to do a little bit of work there to convert them into the same units. So we start off with an old question to show you how this is simply problems that we've done before. What is the probability that a student chosen at random spends more than 8 hours in studying? So one single person. So that's an old problem. They're normally distributed. Okay, the distribution of study times is normal. The mean is 6.42. I want 7 or more with a standard deviation of 1.75. So all of this should look familiar. We get the z-score. So that's 7 minus 6.42 over 1.75. Which reminds, jump back to here and add one more formula that we didn't write over here. So that is the z-score formula, and it's x bar minus mu over sigma over the square root of n, or x bar minus mu over sigma sub x bar. So I kind of forgot to write that previously. It's the same idea though. So in this problem, we'll get a z-score of 0.90, and again, I'm going to use my calculator. Second bars, normal CDF, min, now it says greater than, so my min is 0.9, and my max is 1 and a bunch of zeros, and I get 0.1841. So the area, or the probability, all right, the probability that x is greater than 7 equals 0.1841. Okay, now we're going to ask almost the same question, but we're going to make a slight change. What's the probability that a simple random sample of 4 students will average more than 8 hours? So, again, we know that the sampling distribution is approximately normal with a mean of 6.42. We know that the mean of the sampling distribution is the same as the mean of the population. We want to know 7 or more, but in this case, we're dealing with the standard deviation of x bar because we now have an n equals 4. We're picking 4 students and averaging them. And so we have to recalculate the standard deviation, which is 1.75 over the square root of 4, which is going to give me 0.875. So remember, as soon as I start taking a sample, the standard deviation is going to decrease. The data is less spread out. So I'm going to calculate my z-score, and it still looks pretty similar. And I just realized that I made a mistake up here, which you might have caught. This should have been 8 minus 6.42, and the probability that x is greater than or equal to 8. It won't change the math, but I did write the wrong number there. So back down to this problem, z equals 8 minus 6.42 over my new standard deviation, which is 0.875, and I'm going to get a z-score of 1.81. And when I look that up in the table, the probability that x bar is greater than or equal to 8. Not look it up in the table, but use my calculator. So normal CDF, min, which is 1.81, max, which is 1 and a bunch of zeros, and I get 0.0351. 0.0351, and that would be my answer. Now you'll notice that that area is much smaller. So the next part says compared to A, why does the probability go down? Now first we'll write it, and then I'll kind of show you why that probability goes down. There is less variation in a sample of size 4 than in individual observations. Okay. So now to kind of show what I'm referring to, I'm going to go back to this diagram. Okay. So we'll pick, I'm going to turn this one off, and I'm going to pick n equals 5, which is about as close as I can get. And again, I'm going to pick 5. I average those. I plot them on the graph. I repeat that thousands and thousands of times, and I get this graph. Now notice, again, the mean of the sampling distribution is the same, but it's much less likely. I can get a number out here if I pick one number. But when I pick 5 numbers and average them, it's far less likely for me to get a number that's out there. So when I look at the first one, has an area of about 0.18, all right? And then after I pick a sample, all right, we're looking at this real tiny probability here, which is about 0.0351. Again, averages of samples there's less variation. Okay, so we'll do one more. What is the probability that a student chosen at random spends less than 4 hours studying? So again, this is just an old problem. Mean of 6.42. We want 4 or less. We have a standard deviation of 1.75. I get my z-score, x minus the mean over standard deviation. I get a z-score of negative 1.38. I use my calculator, normal CDF. Now, because I'm going to the left, I want negative 1 and a bunch of zeros, comma, negative 1.38. And I get an area of 0.0838. So the probability that x is less than 4 is 0.0838. And lastly, what is the probability that an SRS of 5 students? Okay, so now I'm introducing a sample. I have n equals 5. There's going to be less variation in a sample of 5, okay, than there will be if I'm picking 1 out of this population. So I have to recalculate my standard deviation, although most of the problem is the same. I have a mean of 6.42. I want a sample of 5 people that has an average of 4 or less. I recalculate my standard deviation, all right? Sigma over the square root of n, which is 1.75 over the square root of 5. And I get 0.7826. I'm going to, again, calculate my z-score, 4 minus 6.42 over my new standard deviation, which is 0.7826. I'm going to get a z-score of 3.09, which is going to give me an area that x bar, the sample mean, is less than 4, of 0.001. So whereas it's unlikely, only 8% chance that I get one person that studied less than 4 hours, if I pick 5 people and average their study hours, it's even less likely to find that their mean study time is less than 4. Okay, so here's another practice problem. What I want you to do is I want you to pause it. I want you to try it on your own, and then check the answers. And here are the answers to A and B. You can walk through the problem. You can see that I recalculated the standard deviation because the sample size in this case was 16. So I recalculated my standard deviation, got my z-score, got the area. And the same thing here, SRS of 20, recalculated my standard deviation, got my z-score. Now z-score negative 8.21 is not very likely, so that probability is about 0. One last thing I'd like you to copy down in your notes, and that is the central limit theorem, which states that when n is large, the sampling distribution of the sample means x bar is approximately normal with mean mu and standard deviation sigma over the square root of n. And that's a big concept in this chapter, and we will continue to talk about it and do some investigations so that that makes more sense.